In this lecture, we're going to introduce acids and bases and the difference between these two. So let's do a quick comparison. And this is looking at a few properties of acids and bases. So acids generally have a sour taste, the ones that are edible. They're going to dissolve metals. They'll also neutralize bases, so they'll perform an acid-base reaction where an acid and a base would neutralize each other. And if we have blue litmus paper, we expect it will turn red, which is one of our nice ways of indicating if we have an acidic solution. Some examples of these that you might have seen already are hydrochloric acid and acetic acid, which we consider basically white vinegar if you've ever just used plain old vinegar in the kitchen, and citric acid, which we find in fruits, but is also an additive in a lot of the processed foods we eat. And for bases, rather than tasting sour, these are actually going to have a bitter taste. And to the touch, they would feel very slippery. So that's a good indication that you have gotten a base on your hand. And if you think about soap, soap feels very slippery and it's very basic. Like acids neutralize bases, our bases in fact neutralize acids. And instead of turning litmus paper red, we'll see it turn litmus paper blue to indicate that there's a base. There's fewer bases that we use in our daily life. Acids we use a lot of, at least when we think of food. But sodium hydroxide is a common strong base. And sodium bicarbonate we use a lot in the kitchen and in the household. And ammonia is used as a cleaning product often. So let's talk about defining acids and bases. Acid, we can give the bronsted-lowry definition. There's actually a few of these. There's also the Arrhenius definition and a Lewis acid base definition, but for this class, we're just going to focus on the bronsted-lowry, which focuses in on what's happening with protons. And acids we consider proton donors, and a proton is really just a hydrogen cation. Hydrogen cations have just one proton in the nucleus and 0 electrons. A hydrogen atom has one proton and one electron, so losing that one electron gives it that positive charge. And then a base will accept a hydrogen atom in an acid-base reaction. So when an acid or a base are reacting, they go hand in hand. So you always have both the acid and the base reacting at any given time. And in these reactions, the acid molecule will donate that hydrogen to the actual base. And here's an example down here that we can see. So here's our acid, and here is our base. And these are just abbreviated. The A stands for acid and the B stands for base. Note that the acid has, no matter what, it has a hydrogen atom somewhere in its structure. And it's a hydrogen atom that will be breaking its bond to the rest of the acid molecule. Now, all bases are going to be required to have a lone pair of electrons somewhere on it. And that lone pair of electrons on the base is going to form a bond by donating both of the electrons to the proton. And so we'll end up with a bond between the hydrogen and the rest of the base. And in this case, the two electrons that are part of this bond both came from the base, but are now shared between the hydrogen and the rest of the base. So the products of this are going to look like my acid minus a hydrogen. And maybe we should write that out because it looks like it's bonded to the hydrogen. And my other product will be the base plus a hydrogen. So it's easy to predict the actual products of these acid-base reactions because we just shift a hydrogen atom from our acid to our base. And this means that the trick is identifying which is your acid and which is your base. So here is that reaction again, walked through typed up rather than me writing it on the bottom. And so let's continue to talk about this idea of how do we identify an acid and a base, and then predict its products. So for an acid, we are going to look for a hydrogen atom every single time. A lot of times, this hydrogen atom is bonded to an oxygen or to a halogen, and that's something like a chlorine or a fluorine or an iodine or a bromine. It can also be bonded to a nitrogen as well, or a sulfur. And typically, although it's not a hard and fast rule, a lot of times when we see an electronegativity difference between these, that hydrogen can act as an acidic hydrogen. Of course, some of our strongest acids, though, do not have polar bonds to that hydrogen. And then what happens is that in our acid-base reaction, as this acid approaches a base, the bond between the hydrogen and the acid right here is actually going to break. And remember, each of these bonds are 2 electrons, and instead of splitting up, so one goes with the hydrogen, one with the acid, both of these become electrons that stay with the acid. And here they are right here. And now my acid is going to have have a charge that's 1 less than whatever it was. So if it's a 0 charge as an acid, it becomes a -1 charge. If it was a -2 charge as an acid, it becomes a -3. If it was a +2 charge as an acid, it becomes a +1. Now our base is going to have that lone pair of electrons, and the requirement for this is so it can create the bond to the hydrogen that has no electrons. And each bond needs to have 2, so they're both going to actually come from the base. So as that hydrogen atom approaches, these electrons are donated to form a bond between the base and the hydrogen. And so here we have that bond right there that forms. And my base now gains 1 more positive charge. And it's kind of, think about it as my base, if it was at 0 and my hydrogen had a plus, now together they have a +1 charge. So if it's a 0 on my base, it becomes a +1 in my product. If it was a -1, now it becomes a 0. If it was a +1, now it becomes a +2. So when looking at a group of molecules and trying to decide which one is actually a base, the trick is going to be that it must contain that lone pair of electrons. So some common ones that we see are nitrogens and oxygens with lone pairs. So ammonium is a nitrogen with a lone pair that can form a bond to a hydrogen. And its product, it adds this hydrogen right here, becomes NH4, ammonium. Another very common one is water or hydroxides, anything with oxygens. Oxygen will have 2 lone pairs at least. If it's an anion, it's actually going to have 3. And these are the electrons that are shared as a base. So some common bases that you'll see are things like sodium hydroxide and potassium hydroxide. These are all very, very strong bases. And they're a metal salt of a hydroxide ion. So that hydroxide ion has the 3 lone pairs on the oxygen. One of these can be donated as a base to a proton to form, here, it's back. I don't know what happened there. To form a conjugate acid, which we'll talk about here in a second. But it'll form a product that now has a new bond to a hydrogen. So to identify a base, look for lone pairs. Now, to identify an acid, really we need to look for a hydrogen. But lots of things have hydrogens. And molecules like, or bonds like CH and CH4, these are not very acidic. They're harder to break. And so really we're looking for hydrogens that are easy to break. And that takes a little bit of chemical intuition. Oftentimes, if that hydrogen is bonded to an oxygen, that's easy to break. Or if that hydrogen is bonded to a halogen, that's also easy to break. So we also see that lots of molecules have more than one hydrogen. And so we can have acids that have more than one hydrogen that leaves and is donated. If there's only one, and a great example of this is hydrochloric acid, we call it monoprotic. Now, if there's two, like sulfuric acid, we call it diprotic. And if it's three, it's triprotic. And these look like, in these two cases here, we have oxygen or hydrogens bonded to oxygens. So here's sulfuric acid, and here's phosphoric acid. In both cases, that oxygen is bonded to a hydrogen, and so it's easier to break. We've been talking about protons a lot, and I do want to take a moment to recognize that a proton is super tiny. It's just a proton without an electron cloud. So in a solution, especially if it's a water solution, an aqueous solution, it's very unlikely that this hydrogen can exist on its own. It's too small and it's too crowded in liquid. So it will quickly run into a water molecule right here. And in this case, water will actually act as a base and form a bond to that hydrogen. And it forms this compound here that we call hydronium. And it has an H3O plus chemical formula, and it's a polyatomic ion. So when we reference protons being donated or accepted, oftentimes this is actually H3O plus hydronium ion when we're talking about things in solution.